So in terms of how many hidden black holes there should be in our galaxy, we predict there should be in total something like 1 million, right? How many we'll actually find depends upon the process that we use, but we should expect there to be of order millions. Set that against how many do we actually know are present in the Milky Way galaxy, and the numbers we predict dwarf the numbers that we observe. So we observe around about 20, we know about 20, and those are confirmed dynamically. So when you have a black hole in a star going around a common center of mass, the emission from the star changes as a function of orbit, and you can work out what the mass of the hidden object is. Through that method, we know of about 20. So 20 set against millions, right? You know, it's massively uneven. So let's go and find those hidden black holes.
So how do we know there are millions of black holes if we've only seen a handful? I think the thing is, we don't really know. We think we understand the physics well enough that we can predict millions. So we have some very, very clever, very, very expensive computer codes called population synthesis. What this does is it brings in the physics that dictates stars, hydrodynamical simulations, and other things that allow us to simulate a population of astrophysical objects. So supernovae, neutron stars, black holes, all of these things. What we do is we start a population many, many hundreds of thousands of years back. We let that simulation evolve on a computer, going through all of those physics transitions that it would do, things interacting, stars dying, stars being born, all of these things. And then when we think it should look like the galaxy should right now, we stop it and we count up how many supernovae there are and how many black holes there are. And all of the other numbers seem about right, yeah, about that many supernovae, about that many neutron stars. But what we're missing when we do our observations are the black holes. Everything else seems okay, but we're missing a huge amount of black holes.
Stellar mass black holes are the much, much smaller cousins of the supermassive black holes. Where a supermassive black hole might have 1 million times the mass of the Sun, stellar mass black holes are about the same mass of the Sun, or maybe a few times bigger. And we expect there to be maybe 1 million, tens of millions of those in a galaxy the size of the Milky Way. And that means that they vastly outnumber the supermassive black holes that you usually hear about. And this new population of stellar mass black holes are what we're trying to find, because we don't know where most of them are. We only know about the ones that are bright in X-rays and a handful of others. That means there are millions of the things that we just don't know about yet, and we've got to find them.
Compact object is like stellar remnant, so it's what occurs when a star has burned all its fuel and becomes like a dead star. And depending on the initial mass of the star, if it's not very massive, it will form a white dwarf, which is very dense compared to what we're used to, but less dense than a neutron star, which occurs when a giant star runs out of fuel, and that's typically the cutoff is typically at around 8 solar masses. So below 8 solar masses, you form a neutron star. But if the star had an initial mass higher than that, normally it would collapse into a black hole. And that's the point where not even gravity can stop the collapse of the core. So therefore you will have a system in which not even light can escape, which is by definition a black hole.
Black holes are black, and that presents one might think, quite an obstacle to discovering them. There are various ways we can do this. So if you have a star close to the black hole, material can be pulled off the star, and you can go around in what we call an accretion disk. It gets very hot, and then we can look with our telescopes to try and find it. But that's actually quite a small number of objects. The reason I want to use optical telescopes to find these things is that, assuming that you have a black hole and a star, that they haven't gone their separate ways following a supernova explosion, there's a probability that they will stay bound together and be orbiting around. And if they are edge on, the light from that star can get bent around the black hole and focus towards us. It's an effect called lensing. So that's what we want to look for, and that light is coming from the star, so it tends to peak in the optical bands. So we're looking for these distinctive shapes that are caused by the black hole transiting in front of the star.
Self-lensing is where we have a compact object and, say, a main sequence star in orbit around each other. So that every time the compact object passes our line of sight, the light appears to be magnified. So we get this periodic brightening.
What you will observe if you're observing this system over time, it's like the brightness will be steady, but suddenly you get this massive increase in luminosity, and this is because the black hole is really bending the light onto our line of sight. And if you detect this periodically, you can be certain that there is a star going around an object that you don't see. And from the profile of this magnification, then you can infer things such as the mass of the compact object, and therefore detect whether this is a black hole or a neutron star.
When people hear about lensing, they typically are hearing about how background quasars that are very, very distant from us, the light from them is being bent around a foreground galaxy or galaxy cluster. So we're talking about massively different scales here, both in terms of actual extent and actual mass. And lensing is very, very interesting. I mean, the principle remains the same, that we have photons that are trying to travel on a straight line, but space-time is bent, so they're forced to move in a different way. So we're looking at lensing on a much smaller scale, and we're looking for a binary system. So that black hole goes around the common center of mass with its star, and it does so on an orbital period. So these lensing events recur.
Because the black holes that we're looking for are basically a whole new population of black holes that we haven't found before, they could tell us a lot about the ways that black holes form and the stars that they form from. So we need to find the black holes that are in wider binaries, the black holes that are what we call quiescent, the ones that aren't accreting matter and feeding from their companion stars, the ones that aren't really bright in X-rays. And that's where we need help. If people can spare a little bit of time, then they can go on the Black Hole Hunters project and help us look for these things, because we do need we need human beings to look at the light curves of these stars to see if there might be a black hole there. It could be one of our volunteers who helps make that discovery, or several of our volunteers actually, because more than one person looks at each light curve. If you get involved, your name might end up on that discovery. You could be one of the people that helps make what could potentially be a huge scientific discovery.